Welcome back to The Explainer. Today, we're doing something a little dangerous. We are stepping way beyond the limits of human intuition and diving into a universe of numbers that's frankly far vaster than humanity ever imagined. We're looking at the cosmic rebellion of infinity, led by two math pioneers who actually dared to map out the uncharted territories of the infinite. I'm talking about George Cantor and Richard Dedekind.
Think about it for a second. 1, 2, 3, 4. We literally mastered the art of counting back in kindergarten. And we honestly thought we had the whole concept of infinity figured out, right? Just keep adding one forever. The end. It's such a nice, neat, completely naive view of the universe. So what happens when a 19th century mathematician comes along and completely breaks the universe? I mean, blowing the doors off the established mathematical world by proving, mathematically, that some infinities are literally, genuinely bigger than other infinities.
Well, this whole revolution started the way a lot of great collaborations do, with a letter to a friend. On November 29, 1873, George Cantor essentially texted his mathematical pen pal, Richard Dedekind, with an absolutely massive question. He wanted to know, could the positive integers, our familiar 1, 2, 3, be put into a perfect one-to-one correspondence with the continuous, smooth line of the positive real numbers? Like, could you actually match them up perfectly, one for one?
And what's absolutely hilarious looking back is Dedekind's initial reaction. He basically blew off what would become one of the greatest mathematical questions of all time. He replied, and I quote, "It did not deserve too much effort because it has no particular practical interest." Honestly, he treated this profound cosmic inquiry into the nature of infinity like a useless weekend Sudoku puzzle.
But, that casual dismissal didn't last long at all. Just look at this timeline from a single week in December 1873. This is literally one of the most high-stakes dramatic weeks in the history of math. On the 2nd, Cantor vigorously defends why his question actually matters. By the 7th, he sends Dedekind a proof that real numbers are actually uncountable. The very next day, Dedekind suddenly realizes, oh wait, this isn't just a brain teaser, and he simplifies Cantor's proof. Then by the 9th, Cantor announces a method to literally construct transcendental numbers. Their rapid-fire back-and-forth correspondence directly shaped the final, totally revolutionary publication that came out in 1874.
Now, to build this argument, Cantor first had to tackle algebraic numbers. Those are numbers that act as roots of polynomials with integer coefficients. He defined this concept called the height of a polynomial. Now, don't let this formula on the screen intimidate you. To borrow a vibe from Richard Feynman, it's really just a brilliantly simple filing system. Cantor realized, hey, if you take the degree of the polynomial, subtract 1, and add the absolute values of all its integer coefficients, you just get a finite whole number. He literally built a finite filing cabinet to perfectly organize an infinite library of algebraic numbers.
Let's walk through exactly how Cantor pulled this off. By organizing polynomials by this height, he systematically listed out all their roots. Height 1 gives us the basic polynomial x, so our first root, x1, is just 0. Move to height 2, and we get the polynomials x plus 1 and x minus 1, which give us the roots -1 and 1. Height 3 gets us slightly more complex polynomials, yielding roots like -2 and -1/2. By doing this, he produced a definitive, orderly sequence where every single real algebraic number appears exactly once. He completely proved that this infinite swirling sea of algebraic numbers is totally countable. You can map every single one of them directly to the basic integers.
Okay, so that's algebraic numbers, but the real numbers also contain transcendentals. These are numbers like pi or e that are emphatically not the roots of those nice polynomials we just talked about. Now, Joseph Liouville had proven they existed 30 years earlier, but his proof was highly controversial. Cantor saw he had two options here. He could use a non-constructive proof, which basically waves its hands and says transcendentals must exist because the math contradicts itself if they don't. But no, Cantor chose a constructive approach for his 1874 publication. He didn't just point to the shadows and say they exist. He gave us an actual mathematical machine to physically build one.
And here is a step-by-step look at how that machine works. It's the 1874 nested interval proof. Imagine you're zooming in on a ruler. First, you take a starting interval, find the first two numbers from your infinite list that fall inside it, and use those as your new, tighter boundaries. We'll call them A1 and B1. Then you look strictly inside that new, smaller gap, find the next two numbers from the list, and squeeze it down again to A2 and B2. You just keep generating these nested intervals, squeezing down infinitely, searching in the cracks between the numbers. And the limit point you eventually hit, it will be a guaranteed transcendental number that avoids your entire original sequence completely.
I want to emphasize that this wasn't just some abstract philosophy for undergrads to ponder late at night in a dorm room. Cantor's 1874 algorithm was a concrete, working procedure. It could calculate a transcendental number to absolutely any required degree of accuracy. And it worked by relying heavily on the supremacy of the least upper bound property of real numbers. Basically, the mathematical guarantee that these infinitely tightening bounds absolutely must converge to a specific, limiting point on the continuous real line.
But as you probably know, mathematics is never static. Fast forward to 1879, and Cantor evolved his own thinking. He introduced the topological concept of a set being everywhere dense. To give you a simplified summary, everywhere dense just means that if you have an interval, no matter how microscopically small you slice it, you are always going to find points of your set sitting inside it. He was essentially shifting the battleground of infinity away from pure limits and moving it right into the fundamental topology of the continuum itself.
Cantor actually realized his first proof could be refined, so in 1879 he split his proof into two distinct cases, depending entirely on whether the sequence is everywhere dense in the interval. If it isn't dense, well, finding a missing number is pretty trivial. But if it is dense, that becomes the more difficult case, and he applied his nested interval logic directly to that specific, highly rigorous topological framework.
But hey, every revolutionary hero needs a villain, right? Enter Leopold Kronecker. Kronecker was a prominent mathematician and editor at the journal Cantor published in, and, well, essentially the grumpy middle manager of 19th century mathematics. He fundamentally could not handle Cantor's expansive, infinite worldview. Kronecker demanded that everything in math be built in strict, finite steps from the natural numbers. He fiercely rejected Cantor's reliance on infinite limits and went so far as to try to delay or downright block Cantor's publications.
So, Cantor needed a foolproof way to bypass Kronecker's annoying complaints about irrational limits, and in 1891 he delivered the absolute ultimate mic drop, the diagonal argument. Imagine mapping out subsets of natural numbers as this massive infinite grid of sequences made up of the letters M and W. You've got row 1, row 2, row 3, and it extends infinitely downwards and infinitely across.
Let's look at the sleek, purely algebraic mechanics of diagonalization here. First, you identify your coordinate system. Then, you walk straight down the diagonal of that grid. Whatever value is sitting on that diagonal, you systematically negate it. So if the first item is M, your completely new sequence starts with W. If the second item is M, your second item becomes W, and so on. By flipping every single item along that diagonal, you absolutely guarantee that your newly built sequence differs from every single row on your infinite list by at least one character. It's brilliant.
The fundamental difference between these two masterpieces is super striking. That 1874 proof, it relies heavily on the topological completeness of real numbers. You know, those nested intervals squeezing down to a limit. But the 1891 diagonal argument, that is pure, unadulterated algebraic sequence manipulation. It requires absolutely zero topological limits. It was Cantor's genius way of entirely bypassing Kronecker's gatekeeping complaints about limits. It's just a totally different airtight machine.
Of course, breaking the mathematical universe doesn't make everyone happy. The famous philosopher Ludwig Wittgenstein later delivered this incredibly scathing quote, declaring mathematics to be, quote, ridden through and through with the pernicious idioms of set theory, and he literally dismissed Cantor's work as utter nonsense. I mean, you can practically taste the sarcasm and the panic there. Cantor's ideas completely broke the brains of the philosophical old guard, who were just desperately clinging to their comfortable, finite realities. But, spoiler alert, Cantor undeniably got the last laugh. If you were taking real analysis right now, you already know his concepts of countability didn't just survive, they became the absolute bedrock of modern set theory. His work on the continuum is the foundation of modern measure theory. It literally underpins the Lebesgue integral that you use in advanced calculus today. And it didn't stop at math. The diagonal method directly led to Gödel's incompleteness theorems and famously inspired Alan Turing's solution to the halting problem in computer science. Talk about a legacy.
George Cantor and Richard Dedekind took kindergarten concepts like counting, and they pulled back the curtain to reveal a staggering cosmos. They showed us that the integers we know so intimately are really just tiny, isolated islands floating in a vast, dark, totally uncountable sea of continuous, transcendental numbers. Which leaves us with one final, deeply profound thought to chew on. If there are infinities literally larger than the infinity we thought we knew, how many other oceans of infinity are out there, just waiting for us in the dark? Keep learning, stay curious, and we'll see you in the next explainer.